Hi, welcome everybody. I'm Matthias, as was said, and I'm working in the area of Logfree programming and concurrency for mainly for autonomous driving and robotics. And today I want to show you some techniques that may prove helpful if you want to tackle similar problems. And the cornerstone for all of this is compare exchange, and I hope it will serve you as well as it does me. So let's take a look at how this talk will be structured. First of all, we have a brief introduction, what we consider real-time systems and what kind of, what Lockfree programming actually is, before we move to looking at Lockfree programming specifically in C++. Then we move on to take a look at atomics and so on, before we look at some kind of case study where we explore a lot of issues that can occur if you are not careful in Lockfree programming. The case study is a so-called exchange buffer, or I call it like this. We will see what it does, and we will encounter various problems there on the way, mainly the ABA problem, which we will solve. And this will conclude the talk, and then I hope I have convinced you that it actually makes sense to use something like this in real-time systems. So that's the main goal, to enable you to use those kind of tricks in real-time systems or otherwise. And you could also call this talk just the journey of Lockfree programming in C++. Okay, what are real-time systems? Real-time systems are systems, which, of course, perform certain tasks, run algorithms. Those tasks are often have priorities and deadlines. Can be periodic, do not have to be periodic. And we have something like a real-time operating system usually, which guarantees that threads are scheduled in some kind of way, but they cannot guarantee that the algorithm the user runs complete on time. Can only guarantee some kind of fairness with regard to that every thread gets an opportunity to do something. That's fairly important because this can help us to guarantee, or to at least allow us to be able to meet deadlines and have system-wide progress in the sense of distributed systems. We distinguish between hard and soft real-time systems. Hard real-time system means, well, if you do not meet deadlines, it's a failure. And that's usually hard because it's hard to come by those kind of execution or time bounds for the execution of runtime of algorithms. And you have hardware effects like caching, branch prediction. You have a very hard time to predict how much time your algorithm will take in the worst case. So that's usually infeasible. But there's also software real-time systems where meeting the deadline, not meeting the deadlines is okay, but it degrades performance, and it should not happen too often, and it also should not exceed the deadlines by too much, which is not too much lateness. So, but how much failure we can tolerate depends, of course, on the application. We are mainly concerned here with soft real-time systems because hard real-time systems are fairly infeasible, as I said, to my knowledge. Of course, in modern systems, we really want to use concurrency because we then get more performance. You can scale our systems further, and by using background threads, you can have increased responsiveness and so on. But if we do this, we immediately face the problem that we have to synchronize access to shared data. And how do we do this usually? Usually we use synchronization primitives like mutex, semaphore, condition variable, and so on. But this leads also to problems, like all those primitives are at the heart blocking, which means if they block for too long, this can lead to lockouts, meaning some kind of processor wants the resource, the mutex, for example, but cannot get it because another one has it, and may even lead to deadlocks, but this is more or less a programming error or the result of a failure. But it can in any case, even if there's no programming error, you can have priority inversion, which means some high priority threads wants to acquire a resource, but it cannot run because a low priority thread, which may have been put to sleep by the operating system, is holding the resource. And so now the high priority thread also has to wait for no real reason. So, and there are other things like starvation, and context switches between threads are of course expensive and so on. So we want to use concurrency, but we also want some kind of, well, those real-time guarantees, or we at least as good as we can. Okay, how can we achieve this? Well, I would propose that Logfree programming may help us here. What, in a nutshell, Logfree programming, the algorithms cannot use blocking primitives like I showed before. It's not entirely correct, or that is correct, but it's not actually the definition. But this has a lot of advantages. We cannot have deadlocks anymore because there's no locking. We have some certain robustness against failures and lockouts and so on. So in a nutshell, we can guarantee progress, meaning doing something useful of at least one thread, regardless of what other threads do. They cannot interfere negatively. And most importantly, we cannot have this kind of priority inversion. And also, but it's not always true, we may hope for less context switches. However, if we do this, there are also disadvantages. So nothing is for free, right? Synchronizing data access becomes harder. The algorithms to do this become more complex. And in the end, it does not even have to be faster than log-based algorithms, but they can. So that's, and we cannot eliminate starvation entirely, but starvation may be reduced if you have some kind of fair operating system scheduling. There are also some step up from this so-called weight-free algorithms, but they are usually more of a theoretical importance because they guarantee more fairness, but they are also slower usually. Okay, so we want to do log-free programming, and of course that's a C++ conference, so we want to do this in C++. Well, I claim that log-free programming is supposed to help, but how do we write those kind of log-free algorithms? If you just have to use, or if you just have those mutexes and so on our disposal, that does not do us much good, right? We need something else. So I would say we need some more friends. Yeah? Okay, and what would those friends be? Well, first of all, we need to think about the basic building block is using atomics. They exist in C++ since C++11. The basic idea is we can atomically access data, and even log-free if the data is small. Because if the data you store in an atomic is large, the compiler may introduce hidden logs for you. We do not want this, of course. There's much to know about atomics. For example, very important, the memory model, which somehow controls in which order different processors can or will see memory operations, like stores and so on. But unfortunately, this is a topic entirely of its own, and it's out of scope of this talk, but we do not need to think about it that much, at this point at least. For our purposes, it suffices that we think of, well, we use sequentially consistent memory order, but that's enough for us. Meaning that in a nutshell, each processor sees memory operations roughly in a similar way as any other processor, but this in turn requires heavy synchronization under the hood. So there are more relaxed and more performant modes, but we will not consider them in this talk. Okay, the basic operations on atomics are just reads and writes, or loads and stores, as it's called for atomics. And there are more complicated operations which also modify the data. As they read something, they modify it, and they write then something. And for example, you can just consider having some atomic X type integer. You store 73, of course, and if you load it again, assuming no other thread does something, if you load it again, you will of course see this value you just stored. You can call something like called fetch add, which is a read modify write operation, where you get the value before and increment the current value. So the result should be 74, but we get back the old value, which is 73. We can, for example, exchange the existing value again with something different, like 37 in this case, and the old value we would get back is 74. And yeah, there are other operators like just increment. Yeah, in some ways they behave like the native types, you could say, which would increase this value to 38. All this happens atomically, but we have not covered the most important operation or the most powerful operation, you could say, and that is compare exchange or compare and swap in the literature. It exists as compare exchange strong in C++, and the basic idea is we have some kind of current value in this atomic X. It's atomic from the previous slide, and we want to exchange it under certain conditions with the desired value. But in the condition is it is still the value we expect. So we have some expected value, and we exchange it. Oh, this is a bit bad. I should maybe set this expected value to something. So of course the call will work regardless. But I don't know what I expect here. So anyway, it works or it does not work, meaning we get, if the exchange worked, we get true, otherwise we get false. So we could think of the semantics as being like this. If we have to model this using no atomic, we could model it like this. We have some kind of value. We have a mutex to get our, to guarantee the atomicity of the operation, basically. And then it works like this, the semantics. As I said, we get an expected value and a new value. Oh, this should not have been a reference and also not const. Anyway, we get a new value and we compare it with the current value. If it's equal, we set the current value to the new value and return true. Otherwise, we just reload the value. That's important that in the failure case, we somehow load the current value into expected. That's important, maybe a bit unintuitive, but it's for efficiency reasons because the hardware already does this for us, and so we do not have to reload it again. But we return false because the exchange failed. The condition was not true. There's also a weak version. We are not too much concerned about this. This weak version can fail even if the condition is true. That can usually be, sometimes if it exists, or the weak version always exists, but it may do the same thing as the strong version. But it may be actually a different hardware operation, which is usually has better performance. But as I said, it can spuriously fail. Again, this is not, of course, done with locks usually for small data. No, there are special hardware instructions, for example, lock compare exchange on x86. And this one is a major building block of all or almost all Logfree algorithms, as we will also see. So let's have a quick look at what we can actually do with compare exchange. So the main usage is often just some kind of looping. I would call it a compare exchange or a compare swap loop. And let's see how this works at a small example. Like we want to create a fetch multiply function, which behaves similarly to fetch add. This function does not exist in hardware, but we can create it on our own with compare exchange and would work somehow like this. The parameters are a bit different here, right? Because we pass the atomic, but of course you could also do this with some kind of member function, and if we have our own atomic and so on. But it's not important. We can we pass the atomic by reference, and we pass some multiplier. It's of course only for the in case, but we could generalize this to other types as well, which support multiplication. And the basic pattern is this: we somehow load the current value. Let's call it the old value, because may already be outdated if something is going on concurrently. We load this old value, and then we perform our local computation on this value. In this case, just multiply the old value with the multiplier. And then we try to exchange the old value or the actual value with our computed result, but only if the old value did not change, meaning nothing else happened in between, basically. Well, it's not entirely correct, as we will see, but the value, for our purposes, the value stays the same, and then this is consistent in some way. We can, we would expect this kind of behavior. And if this exchange works, we break and basically return the old value, as fetch add would also do. Otherwise, we just retry it. It could be, in theory, an infinite loop, right? So meaning starvation would be possible, but you can imagine that this is fairly unlikely, because we always have to somehow lose the exchange, and this will only happen if other threads somehow are always faster than we are. Okay, so that's the first major trick or basic usage of compare exchange to create operations. Let's move on to something more complicated and potentially more useful. And this will be our exchange buffer. Some motivating words, right? The problem to exchange data between threads, I would think it's fairly natural. Well, it occurs very often. Maybe not the most interesting problem, depending, but it occurs very often in multi-threaded programming. And the basic requirement is that we can exchange types, almost arbitrary types, as generic as we can handle. And also we would like to have an arbitrary number of concurrent readers and writers. It should also be allowed that writing to this buffer somehow fails under certain circumstances, but those should be well defined. And what we will introduce to solve this problem is our Logfree exchange buffer. It's useful, yes, but it will just be able to hold one value at a time, so it's a bit limited. But this can be generalized, but it just gets more complicated. But I hope we can, at the end, we can see that the techniques can be used to generalize this to queues and other structures. For now, you can think of it like some kind of limited atomic, which can have some limited operations. No, not all operations within atomic, but it can do it not only for small values, but for generic values and in a lock-free way, which is not true for a regular atomic. Meaning, if it gets too large, compiler, as I said, may introduce locks, which we just do not see. Okay, what would this exchange buffer look like from the interface? I propose certain functions. We want to implement a write function, a try write function, and a take and a read function. Okay, writing means just that. I want to write data into the buffer. I provide the data, and I just get back indication whether it worked or not in form of a bool. It may not work, but only because I'm somehow out of memory in a certain sense. Another operation is try write, which may fail if the buffer already contains data. Can be useful. So it may fail if the data if it already contains data, or if it is out of memory as well. So that can also happen here. And then we have means to access the data in the buffer. And there we distinguish between taking data, which is some kind of a destructive operation because it destroys the data on the buffer. The data is now at the caller side, or we have a read function which just which reads the data, and the data is still in the buffer. For both, we use to return it. To return the value, we use optional because we may return nothing if the buffer currently does not contain a value. It's fairly natural, I think. I favor those kind of functional like constructs, like optional and so on. But this is of course a design choice. It can be done differently as well. Okay, and all of this, of course, has to be log-free, and types should be as general as we can handle. And we do, of course, not want some kind of torn read. We will see what a torn read is later. Meaning we read some kind of garbage which is not even in the buffer. Okay, so let's start implementing this. We'll start with a very simple implementation where we just consider writing and taking the data. We have several assumptions which are listed on the right, but the main point is we store not an atomic to the data, but to the pointer to the data. Because pointers are small, they are on 64-bit systems, they are 64-bit, and that can be handled with log-free atomics. Okay, so that's basically how our class, our first attempt looks like. And how would we handle write then? Well, we get the value. We try to copy the value using invoking a copy constructor. If we get something back, meaning we had memory, get nothing back, we had no memory, and then we fail here. Should be unlikely, but can happen. Otherwise, we just exchange the newly created value, this copy of this, with the old value by calling just exchange. No compare exchange yet. It's better because it's good because this is a less expensive operation. We get the old value back, and if we actually got something, we are responsible for deleting it because at some point we would have created it by writing it previously. Or if we got nothing back, we have nothing to do. In all cases, then the operation succeeds and we return true. So that's simple. Now the opposite side, taking the data, it works like similarly. You just exchange whatever's there with the null pointer, and if you got something back, you can move the data out into your optional. Then you have to delete whatever remains in and now the actual data is now in the optional we are about to return. We return the actual data. Or we got nothing back, and then we have to return null out, meaning nothing. Okay, that looks good, but yeah, it looks also simple. Unfortunately, it's wrong. It's not, and how is it wrong? Well, it's not log-free. Why is it not log-free? Because we are using new and delete, which means we are invoking some kind of allocator, and we cannot expect this allocator to be log-free in all cases. Usually, it will not be. It will be thread safe, yes, but not log-free. So we could not. We would violate our log-free constraint for our structure. Well, that's unfortunate. So, but the message is we cannot use those memory allocators in general unless we really know they are log-free. Then we could. And then it would be that simple for taking at least, writing and taking. Okay, we have to do something about this. And what we do is we take matters in our own hand, and that means we need to consider managing our own memory. And of course, we want to do this log-free. And I will sketch some kind of simplistic log-free memory manager that can be done much more sophisticated, but we can build something from there. Okay. First of all, we will have some log-free storage, which means it's more or less just an abstraction around some array which can hold types T. So you can consider it like some kind of memory pool for objects of type T. And it has certain operations. I will not show how they are implemented, but they're easy enough to implement. So like storing some value at a certain slot. I will talk about slots in this storage. Or freeing the value in a certain slot, meaning calling the copy the destructor. We make heavy use of emplacement new under the hood, but it's also not too important. Or get the corresponding pointer to some index. So we are now moving to work on for the outside interface to work with indices, which has certain advantages, as we will see. And also, for example, access the data at some index, just with the bracket operator. Okay, that's one part. We are separating the storage and the logic to work with the storage. Okay, that's the storage itself. Or the interface. It's easy enough to implement, so we skip this. And then we have something which I call just the Logfree index pool, which manages indices which can be used to access the storage. And the main idea is to access a certain slot of the storage, we have to possess the index. And each slot is either free or used. Initially, they are all free. And well, we have, of course, a constructor, and we can do certain things like getting an index, maybe getting the index, because there may be no free index left, and then we get nothing. Again, we make use of optional. Or the opposite operation, if we are done with using a slot, we will just return the index. So we will kind of call free. Think of malloc and free, but for those kind of indices. And there's no actual allocations. Everything we need is pre-allocated, which also has certain advantages. And all we need to do internally is manage some kind of array of slots, of atomic slots, which we manipulate. But also this, you can hopefully imagine how this works. And I will also at the end provide a link where you can find this. But again, it's most important to just consider that we have such a magic interface. We will use it. And another advantage of indices, we will soon see why these advantages, is they are smaller than pointers. Not 64-bit. In this case, they will be 32-bit. But of course, depending on how much slots we need, we could make this even smaller. So we prefer indices over pointers for those kinds of operations. Okay, what does this help us with our initial problem that our memory allocation, we could not use the memory allocation. Okay, or how does it work? So you can imagine that it works like this, first of all. You have this index pool. Initially, everything is free, nothing is stored. Then you write something at index 0. Okay, you write an A there. You have to obtain the index. Now it's used. You write something else, B, and then it's also used. You write something, you write a C. Now it looks like this. And after you're done with doing whatever you want with B, you delete it or you free it, and then you get, you arrive at this situation. And again, this is only allowed if we have ownership of this index, meaning we own the corresponding memory slot. Now, how does this help us with our problem? Okay, now we move on to creating to repairing our exchange buffer. Observe that we now have some kind of parameter C which controls how many slots we have in the buffer, and not in the buffer, in this storage I mentioned before. And we have something like we have the storage on the one hand, the storage, and the indices to access the storage. And what we also have is some kind of indicator that we have no data, which is now, it's this one. We have some indicator. Just think about it as some kind of logical null pointer. And what we now have, instead of our atomic pointer before, we have an atomic index. And initially, it was, well, before it was initially a null pointer, now it's initially a no data value indicating the buffer is empty. Then again, we have our interface, and that's about it. We also have some kind of helper function. The helper function is just for freeing whatever is in some index, meaning we call this, as I mentioned, this will call the destructor of the value and maybe do something else in the storage if needed, but it should not be really needed. And then it will return the indices or the corresponding index back to the index pool to be, and meaning that the slot is ready to be reused. We will maybe see that the C also controls how much concurrent access we can have to the buffer, or successful concurrent access. We may have as many concurrent access as we want, but some of the operations may fail and would not if we would have a larger value of C. Okay, so the memory is managed by the storage and index pool. We will see how it works. Okay, so now we implement our write operation. And how does it work? We try to obtain an index, and yeah, we may be successful or maybe not successful. Again, it's similar to failing because we are out of memory before. Now we can maybe have no slots left because other writers are occupying them and also trying to write. That's what I meant with the C controlling somewhat degree of concurrent access. But if we get an index, remember this is an optional, then we can of course get its actual value. Then we just call our helper function, which just stores the value we intend to write at the corresponding slot in our storage. This happens here. And after this, we just exchange the current index to, and we obtain with our new one. So we get the old index back. And if there was if there was any data in it, we are responsible now to free it, similarly to calling delete before. We are responsible to free it. Otherwise, we can just return. So we return, we are successful in any case. And we could also do other things like instead of freeing the value, we could imagine that we return the value back to the caller to do whatever he wants with it. But this is, of course, a bit more expensive. And I would propose to have an extra operation for this. This would be writing. And now the opposite operation, taking the data. It looks similar, right? We just have now, we have to exchange, we have to exchange whatever is there with no data, as opposed to the null pointer we did before. And if we get, if we get something, well, if we get nothing, there was nothing in the buffer and we return nothing, that's okay. Otherwise, there was something in the buffer and we move it to the optional, free what remains, and return the optional. We cannot really avoid this move or copy if we want to have some kind of value semantics where we not just give a pointer to the caller, and we, especially with our new self-managed memory, we do not want this because we want to reuse the buffer slot as soon as we can. So that's taking. And remember, well, it's important to think about the order of what happens in free. First, because the destructor, and then return the index. Because as soon as we return the index, it's available to concurrently be reused. And so the order is important. Otherwise, you get nasty bugs. Well, you certainly do not want it because it's hard to debug. I encountered them. Okay. We can also write try write now. That's almost the same. But now we will actually need compare exchange because again, we get the index we write, or if we get the index, we write something in the storage, or what we have, the value we have. But then with try write, we actually expect to have nothing in the index, and we have to communicate this somehow. And we do this with compare exchange here. We expect that there's no data, and we try to exchange no data with whatever we wrote before. If this succeeds, there was no data, and we return true. Otherwise, there was data, and our operation fails. But before we return false, we have to free what we allocated, because otherwise we would have occupied the slot and we will run out of memory, and that's bad, of course. So, and we are allowed, or the semantics of try write are, we are allowed to fail in this case. So, because we just want to write to an empty buffer. So that's try write out of the way. That's also, I think, fairly nice. And how does this work? You can imagine it works somehow like this. Now we have the index pool, we have the storage, and we have the current value of our atomic. Initially, it's no data, of course. And now we write the U. Well, we obtain the index 0. We write something to the storage. So we write U to the storage, and this write completes. We write V. So and after writing of V is completed, we of course have removed U from and just use this new index. And now the index is 1. Now we can consider that some kind of take operation occurs, and then of course everything is free again, and we arrive at no data again, and we are back where we were before. And now consider that, for example, simultaneously or concurrently, we have writing of X and Y, and one of the operations will complete first, and let's assume that it's writing Y, and then the situation would look like this. X is already written to the storage, but the operation is not complete, and that is also an important point, because the operation, you could say the operation becomes observable for other threads as soon as the compare exchange succeeds. And that's the case here for Y. So at this point, it becomes observable. And if you consider that writing X will also succeed a bit later, then it would switch. Then we would have X to be the content of the buffer and 0 the index. Anyway, so that's hopefully illustrating how this kind of writing here works and how At the moment, compare exchange was only important for try write, remember, but we have not faced the real challenge, right? It all looks fairly nice, but the real challenge is actually read. Taking data, it looks rather simple because compare exchange or change are like made for it. We transfer the ownership. But what if we now want to read the data without taking it? That's much harder without locking, like in mutex. But let's try it anyway. So we try first. Let's see what happens if we just do it naively. Well, let's think about we load the current index. If there's nothing, okay, then it's fair enough to return nothing. Otherwise, there was something. We just copy it to our optional, doing so, and return the value. We could do this, but that has a very, very bad bug, right? Well, it's wrong because we cannot really. We have to assume that concurrently someone may change the value in certain ways by calling the write operation or the take operation, and then bad things will happen. There are many possible outcomes, but one outcome is, of course, we read the correct value, which we want. But other outcomes are we are reading the value while it's being manipulated, which leads to a turn from read, or we could even crash because the update is not complete. And you may think of what happens if you have a stood list and some pointers are being manipulated in the stood list, or the object is about to be deleted, or the constructor is running, or already was deleted, and we access this, all kind of bad things happen, basically undefined behavior. So we need to be aware of the data that can change concurrently. We cannot just simply read it just like this. First thing to mitigate some of the problems is to restrict our data type to be trivially copyable, meaning that our copy is essentially a mem copy, and then we at least do not have some kind of unpredictable questions. Of course, it's a very very strong restriction of the data type we use, but it's still useful. So we cannot have crashes, but the data can still be concurrently modified. And well, we have not solved our problems like this. From now on, we assume that we have a trivial copyability. Okay, now let's use compare exchange again to try to check whether the data changes in the meantime. So let's have a look. Well, what can we do? We can just call. We can read the data now in the loop. If there's no data, we just return as before. Otherwise, we read it, and immediately after we're done with reading, we call compare exchange with, well, both arguments are the same, which means we check whether the index is currently or has not changed. And if it did not change, we assume nothing happened in between, and our read is valid. So that's, yeah, otherwise we have to try again. It looks promising. Unfortunately, it's also not quite correct, because we now have a new problem called the ABA problem. And in a nutshell, it means the index value may have changed back and forth where we are reading. And of course, equal indices do not necessarily imply that the values are still equal or were equal. Even if they are equal afterwards, they may have not been equal between those operations. So we need something smarter. Well, how would this look like? Well, consider that the situation is like this, and you want to read it, and the read is this is the situation, and the read is interrupted here. You write something, now you have this in the buffer, 2 x's. Then you write again something, you have 2 y's in the buffer. Now it's the same slot you were initially reading, and then the read completes. But in the mean, it changed, the content of the slot 1 changed from 2 u's to 2 y's. And now we could have read, for example, we could have read the old w, okay. We could have read 2 y's, that's probably what we want, but we also could have a torn read. We read some kind of weird mixture of the data, which was never in the buffer at all. And that's the ABA problem, and the A, B, and A are on the indices here, right? We change from 1 to 0 to back to 1 when we are now checking again with the compare exchange. And read complete means the compare exchange is successful. Okay, so we have to solve this problem somehow, but how do we do this? This is fairly hard. We need an idea is we could try to count whenever we write a value. Let's see. And we need something which is the ABA count. I really liked this guy when I was a kid, so he has to be here. It's counting stuff, right? So do we. Okay. Now it looks a bit overwhelming, but actually it isn't, because what we now do is we introduce an extended version of our index, which contains not just the index, but this counter, that's this ABA counter, right? And there's a concept like pointer tagging, and so I call it also tagged index, where in the pointer tagging, you just use some not used bits to indicate certain states. And this is exactly what we are doing here as well, because we are adding to the index some counter, and the counter is initially 0. And we can also check that this data structure, and that's important, is not too large to be used in a compare exchange operation with this static assert here. It's available from C++17 onwards. So otherwise, the definitions are the same. And now let's take a look at how this helps us. The idea is always when we modify, meaning writing and also taking, but write something to the buffer, we want to increment the counter as well. And so we can detect concurrent changes. Because compare exchange now, we have now, instead of the index, we have this tagged index in the atomic. And compare exchange will work on both. It will only compare to equal if both did not change, index and counter. That's the basic idea. Okay, so writing the initial phase is the same as before. Maybe we get an index, now we have to do some tricks with this tagged index to get this into a tagged index, and we have to store again our value before we move on to do the compare exchange loop. And the idea is just, well, we take the old counter, we have it because we have loaded the value, and the index is frozen to the value we want to index we want to set, right? It's depending on what index we got from the pool, but the counter is set to whatever was in the counter before. So now we to plus one. So we want to increase it by 1, and we try the compare exchange. And again, if this did not fail and we got data, there was data and we have to free it, and then it is successful. Otherwise, we just retry and so on. So that's writing with an AdaCounter. And remember, the compare exchange operation only succeeds if the counter and the index are not changed. So, and the idea is that the reader can now use this to detect it. Taking the data is also similar as before. You can think of taking the data like writing nothing to the buffer, and instead of in returning whatever is there. So again, we have to load what is there. Now we have to use compare exchange. We increment the counter, we try our exchange, and if it succeeded, we know that there was something in the buffer. Otherwise, we would not have arrived here in this compare exchange in the first place to this loop condition. And then we just free the internal value, so calling it destructor basically, and return what was in the buffer. Otherwise, compare exchange fails, and that can mean either the counter changed in between, or the buffer got empty, and then we just stop this looping. And now we are in the position that we can read with the AdaCounter, and the read code essentially did not even change at all. The auto values would have sometimes now have tagged indices, but that's about all. And we can use the same code as before, and now it actually works because now the compare exchange considers the counter as well. So yeah, that's essentially it. Consider that the concurrent writes are happening, the counter changes. Concurrent takes are happening, the counter changes as well. And if some mixture of those happens, the counter also changes. And so the compare exchange will fail if anything happens in between. There's also some topic of this counter wraparound. We will not consider this. It's really unlikely, but we can mitigate this as well, but we cannot go there today. Okay, we can use those monotonic counters to detect concurrent changes. That is quite important. And now we have solved the ABA problem in our case, up to this wraparound, of course, which I was talking about. So the picture now looks like this. We are from 1 to 0 to 1 again, but the counter increases as well. And so the only possible read result we can have is 2 Ys. And we can have no torn read anymore. And that's, well, and now we have implemented our complete interface. There remain some kind of things like, if you could say, well, you are using optional, and optional, as you may know, will allocate dynamic memory. So we are, for the same reason we had initially, it's not entirely lock-free. But this can be resolved by replacing the optional with something using no dynamic memory. That's possible. And of course, we have the requirement on our type that T must also, the copy constructor cannot use locks or something. It must be lock-free. But we already moved to trivially copyable T's, and so it uses memcopy, and memcopy is lock-free. The basic message is a function can only be lock-free if all functions it calls are also lock-free. So I think that's fairly clear. Well, we have another restriction which I not actually like, but I think we cannot really easily get around. This is this construction that we have to use trivially copyable types. Of course, we only have to do this if we want to be able to read. If you want a restriction of this buffer, we just want to write and take. You do not have to do all this, also not do this with a counter and so on. And type can be more general. But if you want to read, can we drop this restriction? The answer is yes, but we have to solve a much more complicated problem, which is called safe memory reclamation. Of course, we have to solve it in a lock-free way. And there are ways to do this. That's not that recent, but so hazard pointers. And the idea is we need to somehow keep track of the users of our memory before we allow other concurrent operations to reuse the memory. And which this boils down to implementing lock-free garbage collection. And our friend and helper here will be as well compare exchange. So there's not really a way around this. Compare exchange is very powerful, and yeah, but implementing this is of course out of scope here. We have also, initially I talked about memory order. In our examples, it was all sequentially consistent by default. Usually you can relax it somewhat. In many cases, acquire release is enough, but I would strongly advise that we only optimize the memory order once the algorithm basically is working, because there's no way that the algorithm will work with a weaker memory order if it does not even work with a stronger one. It's nothing short of a miracle. Pure luck. It cannot. You are measuring probably wrongly if you observe this. So first get it right with sequentially consistent order, and then move on to tweak the memory order to something more. And that is beneficial because sequentially consistent is very expensive. If you can get away with weaker memory orders, that's nice. Okay. What does all of this help us in real-time systems, to sum it up? As I said, we avoid deadlocks and priority inversion, and also at least consider you have no competing threads, and at least one thread will make progress because they are not blocked. They may only fail if another update lets it compare exchange fail. That's not blocking, that is starvation. And individual threads may starve, right? But we can even do something about starvation. We can sketch some ideas here, like we could add some kind of timeouts in our operation. Of course, we cannot interrupt our operation at any time. That's a bit asking too much, but we could, after a failure, look whether we exceed some deadline, and if so, we could return. So with some kind of error indicator. Other termination criteria are conceivable as well, of course. And you can even to improve the fairness, because as I said, if many threads are running and doing compare exchanges, sometimes, theoretically, one may starve. And to reduce the chances of this happening, you can introduce some semi-random sleeps and more sophisticated methods. And where you arrive is essentially making your algorithm in a way wait-free, but you pay for it. You pay for it, and everything gets slowed down by this additional logic and sleeps. It gets more fair, yes, but it also gets slowed down. So it's useful for real-time systems, I would argue. Or it depends on your use case. you may be able to, I think it's fairly clear that we can try to generalize this to queues, stacks, caches, and so on, because the exchange buffer is just any of these structures with some kind of capacity 1. But then we encounter more problems like, how many concurrent readers should it allow, concurrent writers, and what is the size of internal buffer? We need to deal with things like the read and write position in the buffer, or consider what should happen if this container overflows. And we may even encounter a problem which I would have liked to present, how we can update multiple locations atomically without corrupting the structure. That's a fairly unique but a bit more advanced technique. Many new problems arrive, interesting problems, I think. And I'm involved in developing this Isorix zero copy middleware, and there we actually use zero copy means we transfer memory efficiently, and there we between processes in this case, and there we use actually Logfree queues, not this exchange buffer, but Logfree queues, which is a step up from this, and also have Logfree shared memory management. And you can use this in high safety applications. You can, it's very fast, and so it's suitable for real-time systems. And for example, it also comes with some utility library. And this, for example, contains this optional without using dynamic memory. So we could solve our remaining problem with this as well. So that's, I would argue, some kind of real-time applications. I can consider others as well where we can use those techniques, but finally, I said the algorithms are getting more complex. Testing algorithms is generally hard. It's harder if concurrency is involved, because threads can interleave in many ways, and it's even harder if it's concurrent and log-free, because you do not even have some kind of guarantees with critical sections where you can say, okay, only one thread can be here at this time and so on. So that's harder to argue. You cannot do this. Well, I have no recipe to guarantee correctness. Would like to hear one, but I don't have one. But what should you do if you develop those algorithms? Well, you need to define the algorithm properly, or what you want from the algorithm. Then you devise the algorithm theoretically. Then you can prove the correctness. There are even theorem provers for this, like check out TLA plus and things like that. And you can implement it in C++ or otherwise. Review the code, hopefully by experts, so people know what they are doing, because it gets complicated or tricky fast. You need unit tests. Then you need stress tests. And finally, you need to instrument, or you may consider instrumenting the code. I do not quite like this, but it's an option. And then there are other tools like verification with CPP-mem for small snippets. But in general, you can only disprove correctness with those kind of methods, but still it increases your confidence in the correctness. Okay, so I'm a bit running out of time, I think, but now we have hopefully seen that our new friend Compare Exchange allows us to do interesting things and to implement algorithms in, especially for data exchange, but there's many more things. And well, the key observations we have already seen. So, but remember, there are disadvantages. It's rather expensive, but logs with contentions as well. But more, consider the complicated algorithms more of a disadvantage. It can be subtly broken. Maybe what I showed you is even, it's also subtly broken. I'm not aware of this, but I cannot rule it out. And they are hard to test. And to finalize all this, you have to keep in mind that Compare Exchange is a very powerful operation. Because it solves the so-called distributed consensus problem, and you can use this kind of theoretical result to practically make synchronize access to any concurrent object. So that's a very general. There are very general results, and we can of course implement all those things in C++ as well. Okay, that about sums it up. You can read more about, for example, how it's used in isolix, and you can have a look at the queues there. Here, can find this exchange buffer there. Sorry, it's not entirely cleaned up, but the implementation and some tests are there. And also a bit, the code pieces which shows this kind of concurrently updating multiple locations. And I highly recommend reading this book here, because I learned a lot about practical multithreading there, and so there are not many books about concurrency in C++. So with that being said, thanks for your attention. And if there are any questions, I'm of course happy to answer them. And I strongly encourage you to devise your own Logfree algorithms. And finally, I have to really thank my colleagues, Bob and so on, which you may not know him, but he's also involved in the isolix project, which I had very useful discussions for this talk. And he pointed out many small issues in the code. And also my brother. Okay, I also showed the code to him. Thank you. Any questions?
So, okay, thank you, Matthias. I think we're really running out of time.
Yeah.
The most voted question was about the testing. How is it tested? But I think that was a lot focused on the last pages. So I would guess it would be the best to have a discussion on the table, on the launch table, so that you can interact with each other. And so please be at the table, and then you can directly speak with Matthias. So thank you again. Very nice presentation, and we'll see you at the table.
You're welcome. Bye.